Welcome to the course Business Analytics and Data Mining Modeling using R Part 2. So, in previous lecture we started our discussion on regression based forecasting methods. So, therein we talked about the importance of modeling trend and seasonality. We started our discussion with trend. We talked about three specific trend shapes, linear trends, linear trend, exponential trend, polynomial trend. We also did an exercise in our studio environment where we were able to model the linear trend and exponential trend. Now, in this particular lecture we will start with the third type, that is polynomial trend. So, let us discuss this and then we will go back to our studio environment and we will model this. So, if we look at the polynomial trend, so specifically we will focus on the quadratic trend. So, quadratic relationship, if it is there, it can be modeled as below. So, the equation we can have a look. Y t, and on the RHS side we have beta 0 plus beta 1 t plus beta 2 t square plus epsilon. So, we can see now we have two two predictors here, t and square of t, and so these two predictors. So, our if we talk about the specific data set that we are using, bicycle ridership. So, y being the number of riders. So, now number of riders is going to be regressed on these two variables t and square of t, where t is the time index. So, the additional predictor that we have t square, which is essentially to capture the quadratic relationship. So, when we use this quadratic term t square, essentially what we are expecting is that series is following a U shaped trend. So, if we remember the plot of the original series, then the kind of trend that was visible there, it looked more like a U shaped trend instead of linear or exponential trend. So, this model particularly fits a multiple linear regression of number of riders on two predictors, as we discussed, time index and square of it. So, we will go back to the RStudio model, RStudio environment, and let us try and build this polynomial trend, rather quadratic trend. So, first we will compute this new predictor, that is t square. So, we call this t sq here. So, now we are multiplying these two value t in we had already computed time index. So, now we are going to multiply it with its own value and we will get the t square. So, let us run this. Now, we are going to append this new variable into the existing data frame that we have. So, let us have a look at first 6 observations. Now, we can see here we have the t square has been added. So, in the quadratic modeling that we are going to perform, we will have t and t square, and riders is also there. So, we are going to regress this riders on these two predictors t and t sq. So, just like other modeling that we did, next we are going to trim this data set. So, we will create these two partition, training and testing. You can see we are using the same numbers of observation that we had used for earlier models. Now, we will look at the model equation. So, the formula says riders versus t plus t sq. So, now in this quadratic model we are regressing riders on these two variables, and the data frame is also appropriately specified. So, let us build this model. It has been built. Let us have a look at the results. So, if we look at the result here, we can see t and t square, and we can see both seem to be significant here. So, this model is also significant. So, if we are able to remember the linear trend and the exponential trend, that modeling that we had done in the previous lectures, they were also found to be significant. This one, which is the quadratic model, is also found to be significant. Now, we will compare how the performance, we will compare the performance of this particular model with the previous models as well. So, first let us score the test set. So, you can see model object mod 2 and the test partition. So, let us score this off. Now, let us compute the matrix numbers. So, we can see here these are the numbers for training partition. So, RMSE value comes out to be 149. So, ME value is quite close to 0. Let us compute these metrics for test partition. So, you can see the value is now 136. So, it seems that the model is performing well on validation partition, rather the model seems to be performing better in validation partition in comparison to what we had its performance on training partition. So, if you remember the two other models candidate models that we had run in previous lecture, the linear trend and the exponential both had RMSE value of more than 200 on test set. However, if we look at the this particular model, the RMSE value has come down to 136, which is even smaller than its RMSE value on training set. So, it seems that not just this quadratic model is significant, it is also adequately capturing the time series pattern. So, we will confirm this. So, let us plot actual series using training set. So, again just like previous models, we will create this time series, we will subset this time series object, and then let us plot this. So, this is the plot, this is for the training training set, and now we will just add the fitted model that we have just estimated. So, first we will extract the time index from it, and then we will use the points function, and the fitted values are going to be plotted. So, now we can see here, let us zoom into this plot. So, we can see now this U shaped curve has been fitted, this quadratic curve has been fitted on the time series, and we can see it seems to be adequately capturing the shape of trend that is there in the time series, and which actually also got reflected in the results on test partition. So, let us have a look at the residual series. So, we will plot this one. Now, if we look at the residual series, now we can see here just we remember our modeling for linear trend, the residual series plot actually was carrying the U shaped trend along with it. Now, in this residual plot we do not see any trend here. So, that has been adequately captured by the model itself, and it seems that only the seasonality is left over in this residual plot, because we till now we have not modeled seasonality component. So, let us go back to our discussion. So, three types of trend shapes till now we have been able to model: linear trend, exponential trend, and polynomial trend. And we saw that how even though the linear trend and the exponential trend were found to be significant, but there was significant gap in terms of performance on a test partition test set. And when we looked at the polynomial trend, the quadratic trend, the performance improved on the test set, and the shape of the trend that was present in the time series, original time series, that was adequately captured, and the same could be confirmed the same was confirmed by the residual series plot. So, let us move further. So, till now we talked about these three types of trend shape. So, is it possible to fit other types of trend shapes? So, yes, that can be done, but certain points that we need to discuss here. So, fitting other types of trend shapes, so it can be done if this particular trend shape that we want to fit, it can be expressed in a mathematical form, just like the linear trend. We had a mathematical form, the equation that could be used to model it into using multiple linear regression, and then for the exponential trend also, and for the polynomial, that is quadratic trend that we had used. So, if we want to fit any other type of trend shape, and if it can be expressed in the mathematical form, definitely it can be fitted. However, from modeling perspective, we need to take care of certain things. For example, the shape that we want to fit, it should be applicable for the entire series as well as future observations that are to be forecasted, because the main idea is to be able to forecast future values. So, therefore, the shape that we are that we plan to fit for the series, it should be applicable for the entire series and also the future observation that we want to forecast. Only then the model is going to perform well. So, you can also see one small point is also mentioned here, should be global. So, like we will like to refer back to our earlier discussion when we talked about that if we plan to use statistical method on the model driven approach, where we are using regression based kind of methods. So, there the kind of trend that is there, the kind of patterns that are available, they should be global in nature, so that the model is able to perform well on the not just on the points which are part of the training, but also on the points where we want to forecast future values. So, keeping these things in mind, from the modeling perspective, the trend shape should be applicable for the entire series and future observation, and the trend shape, if it can be presented in a mathematical form, then definitely we can fit it using the approach that we have discussed in previous and this lecture as well. Another point related to this is that if we happen to select an overly complex shape which seem to be fitting the training data. So, sometime we might think about a shape which could be represented in a mathematical form and is also look to be fitting to the training data points, but this can lead to overfitting because the future points might not be following this particular shape. So, therefore, using an overly complex shape typically can lead to overfitting and also poor performance on validation set, because that shape, even though it might be fitting the training set observation quite well, but it might not be applicable for the validation set points or even for future observations. So, therefore, we should avoid selecting an overly complex. Rather, the more important point is we should look for any shape that we want to fit, we should look whether it is going to be applicable globally for the time series, for the period of time series under consideration. Let us move forward. So, till now the modeling that we have done was mainly about the trend component. So, seasonality patterns were not modeled. So, now what we are going to do is we will discuss the this particular aspect, modeling the seasonality. So, let us understand a few points about this. So, what is seasonality? So, though we have discussed this in previous lectures as well, let us discuss it again. A seasonal pattern in a series means observations for particular periods or seasons have consistently higher or lower values in comparison to other periods. So, as we have talked about in previous lectures, we are going to observe certain peak values which are consistently higher in comparison to the average level values, and this appears repeatedly. So, for certain periods the values are consistently higher every time that that period or season comes again, the values that are being taken there, they are higher or lower consistently from the average level. So, observations for particular periods have consistently higher or lower values in comparison to other periods, then we can say that probably some sort of seasonality is present in the series. For example, day of week patterns, monthly patterns, quarterly patterns. So, what we mean by these examples is that if the series is weekly, then for particular days the values could be higher. For example, for Sundays and Saturdays, the values could be higher in comparison to the working days. So, this is what we mean. Similarly, for monthly patterns, it could be like that for a month of May and June, which are the summer months, the values could be higher in comparison to other months in the year. Now, the next one, quarterly patterns, what we mean is for a particular quarter, for example, let us say April, May, June, the values for this particular quarter might be higher in comparison to the other quarters. So, this is in this fashion the seasonality could be present in a particular series. Now, seasonality could be of two types. The way those values are consistently higher or lower, it could be present in two ways. So, let us discuss these two types of seasonality. So, first one is additive seasonality. So, what we mean by this is that values are higher or lower by a certain amount for the particular seasons in comparison to the other seasons on an average level. So, it is the additional amount by which the values are either higher or lower. So, in comparison to other seasons, the seasons where we are saying the seasonality is present, the values are higher or lower by a certain amount. So, when this is the case, we say that the additive seasonality is present. So, typically when we are modeling this kind of seasonality, y is our output variable. In the other kind of seasonality, which is the multiplicative seasonality, the output variable will change to y. So, why this is going to happen? Let us understand what multiplicative seasonality is. So, in multiplicative seasonality, values are higher or lower by a certain percentage for the particular seasons in comparison to other seasons on an average level. So, the particular seasons, particular periods where we are observing seasonality, the values of those seasons seem to be higher or lower by a certain percentage. So, because of this, the nature of the seasonality is going to be multiplicative. So, we can say higher by by a factor of 1.2 or 1.1 or 1.05 or 1.3. So, because of this kind of this kind of variation due to seasonality, we say this we call this as multiplicative seasonality. So, in this case, as we have seen in case of exponential trend, that we had taken log of y as the output variable. Similarly, because of the multiplicative seasonality, we will have to take log y as the output variable to be able to use the multiple linear regression model for fitting this kind of seasonality. So, what we are going to do next is we will take our bicycle adhesive example and we will model additive seasonality, where values for a certain period where we are expecting seasonality, they are going to be either higher or lower by a certain amount. So, what are the steps that need to be taken to implement this? To implement this additive seasonality, to model this additive seasonality. So, first thing, we need to create a new categorical variable. So, main idea about creating this categorical variable is to record the season for each observation. So, for each of the observation that is there in the time series, we would like to record, we would like to note down the season for that observation, the way we can name it, the way we can identify it. So, once that is done, so there are going to be a number of seasons for the specified period of time series. So, if there are m seasons, so this categorical variable is going to have m labels. So, therefore, we are going to we will have to create m minus 1 dummy variables, and these dummy variables are then can then be included in the regression equation as predictors, and that is how the seasonality can be modeled. So, what we will do, I will go back to our R Studio and will try and model this seasonality into our time series forecasting. So, let us load this library. So, we are going to import this data set first, bicycle ridership. So, once this data set is imported, we will see that as I talked about, we will first create a categorical variable to record this seasonality for each of the observation. So, there seems to be some problem here. So, let us stop this. There is a small stop button, as you can see in this particular console window. So, we will try and stop this because it okay. So, we will try it again. So, let us load the library, let us import the data set. So, you can see the data set has been imported. We can see in the environment section 159 observation, 2 variables. So, let us run this code as well. Let us have a look at the structure, same variables. This is the bicycle ridership data set. Now, what we are going to do is we will create this new categorical variable seasonality. So, you can see in the next line of code I have season here, and I am calling this format function which we have used in previous lectures as well. So, month dot year, this particular variable, now this is going to be formatted using this particular function, and we will just have the month. So, we will just have the month for each observation. Now, since this is monthly time series, and what we are expecting is that the seasonality is month wise. If we remember the time plot of the actual time series, we saw that there were few ups and downs for a few months. A few months the ridership was significantly higher in comparison to other months. So, the seasonality looked to be monthly, and for the same reason this in the season variable, categorical variable, we are going to record the month as season. So, using this function, we would be able to capture the month for each observation. Had this seasonality been a quarter, for some certain quarters, the number of riders would have been significantly higher in comparison to the other quarters. Then we would have captured the quarter here in this season variable. So, we can have 12 months in a year. So, total number of variables that we expect, total number of labels that we expect in this categorical variable are going to be 12. So, let us create this variable. Now, we are going to append this in this our existing data frame. Let us have a look at first 6 observations. We can see here the second column is riders, that is number of riders for each month, and then we have season. So, which is capturing the name of the month. So, this is because we are expecting the monthly seasonality. So, for this reason we have captured the same in this categorical variable. Now, as we have done earlier also, and the next step is going to be trimming of a data set. So, let us create the training set, which is the earlier period, first 147 observations, and then the remaining 12 observation for the test set. Now, if we look at the model, we are calling the LM function, and you see that we are modeling regressing riders against season. So, you can see we are not including time index here. We are just trying to model only the seasonality component, though we have understood from our previous from this lecture and previous lectures itself that the trend is present, and we were able to see the results also that quadratic trend was able to adequately capture the pattern. However, in this exercise we are only focusing on the seasonality component, and that is why in this equation riders is being regressed as against season, right, and the data set data frame is appropriately specified. So, let us build this model. Now, have a look at the results. So, now as we know that for any variable which is factor will have the these dummy variables created internally in our environment, and you can see in the results all these all these dummy variables are there. So, we do not have to explicitly do it in our environment. So, you can see season August, season December, season Feb. So, total these seasons 11 seasons are going to be there, one is going to be one might be there for the reference. So, now if we look at the results here, so August this season seems to be significant, then Feb is significant, then Jan is significant, and here we can see that July is also seem to be significant. Any other season, let us scroll down. So, we can see that September is also significant. So, it seems that July, August and September, those 3 months they seem to be significant, and Jan and Feb are also seem to be significant. So, these are the months which are having significantly higher or lower value depending on the estimated coefficient. So, if we look at the estimated coefficient here. So, for August it is 139. So, it seems that for August which is significant, the values are on an average level higher for month of August by 139. If we look at the Feb and Jan, so the values are on an average level lower by for Feb it is lower by 288, and for Jan it is lower by 251. So, for some months values are higher, some months values are lower. So, for the month August it was higher. Now, we look at the July, it is also on the higher side. We look at the September, it is on the lower side. So, it is July and August where the August is having more higher level of significance. The values are in particular on the higher side, and also in July. For month of Feb and Jan, values are on the lower side, and also for the month of September, values are on the lower side. So, we can see for certain months values on the higher side, for certain months values on the lower side. So, now let us score the test data set. Now, what we will do is we will compute the matrix for these two sets. So, let us have a look at the numbers. Let us compute for test set also. So, you can see the RMSE value is 264, which is on test data set, which is higher in comparison to previous other models that we had built using linear trend. It was about 210, in exponential it was also about 210. For the polynomial, the quadratic trend, the value came down to 130, 140, and this value has gone up. This is about 264. So, it seems that even though the seasonality is present, we saw that a few dummy variables were significant. Modeling just the seasonality component actually is not good enough to capture the patterns in the series. So, this is what we understand. So, we can confirm the same using other plots. So, let us create the time series for the training set and plot it. You can see here in the plot section. Now, we will plot the fitted seasonality. So, first we will compute the time index and we will add the fitted points. So, we can see here, let us zoom into the plot. So, we can see that seasonality has been fitted, red lines have been used, and we can see that those swings are being adequately captured here. However, the trend is not being captured, and that is what is resulting in higher error for this model, seasonality only model. Same thing we can confirm if we plot this residual series. So, we will see that if we look at the residual series, you can see that U shaped trend that we were able to adequately capture using the quadratic model. Now, this is part of the residual series, that means it was not captured using just the seasonality component, and it has become part of residual series. So, what we need to do here is that probably we need to model both trend and seasonality. So, quadratic model was able to capture the U shaped trend that was clearly present in the series, and the seasonality we have seen that monthly seasonality is present for some month it was the dummy variables were clearly significant. Therefore, we need to model both trend and seasonality, the quadratic trend and seasonality. So, let us go back, and now in the next model that we are going to create, we will model both. So, let us first compute these two predictors t and t square. So, we will compute t and t square like we did in previous lectures as well. We will add these two variables in our existing data frame. Let us have a look at the first 6 observations. Now, in this data frame we have riders, season, t and t square. Now, next step is typically trimming, training set and test set. Now, if we look at the model equation here, we are regressing riders against t and t square plus season, which is the categorical variable. Now, we will build this model. Let us look at the results. So, we can see here September is now significant, October, November is also significant. Now, this is happening because of the presence of two predictors t and t square. We can see now that July, Jan, Feb, these two were earlier significant as well, but for July the significance level has gone up. August is significant again. So, seasonality is significant, seasonality is present. Now, t and t square are also significant. So, it seems that this model is going to perform quite well. So, let us check that out. So, we will score the test set. Now, let us compute the matrix. So, first training partition and then test partition. Now, let us have a look. The RMSE value for training partition has also come down, and RMSE value for test partition has come down. So, we look at the focus on the test partition, the RMSE value has come down to 49. Remember the best RMSE value till now that we had was when we model the quadratic trend, it came down to 136 something, and now when we model both quadratic trend and seasonality, now this RMSE value has come down to 49. So, it looks like that the model has improved significantly, and the same thing can be confirmed using some of these plots. So, we will create a time series plot for training set. So, this is the plot. Now, let us look at this, let us fit the fitted model which has a quadratic trend as well as seasonality. So, we will fit this. Now, let us zoom into this plot. Now, we see that the fitted model in the red line and the actual series in the black. So, we can see the swings are being captured, and the fitted model is also taking that shape of the actual series. So, it is of course, it is not perfectly fitting the actual series, but now it is closely resembling the actual series. The red line is closely resembling the closely following the actual series. Same we can confirm by plotting the residual series. So, let us run this code. So, this is the residual series plot. Now, if we look at the residual series plot, we can see no extra pattern or something clearly visible. So, random variations seem to be there. So, it seems that we have been able to adequately capture trend and seasonality and therefore, the model. So, with this we will stop here and we will continue our discussion on regression based forecasting methods in the next lecture. Thank you.